Hello, everyone, and welcome to this episode of DeepTech Studio. The European Research Laboratory for Particle Physics, CERN, is a name synonymous with the advancements and research in particle physics. The research at CERN hopes to hold answers to the questions of what forms the universe's building blocks. CERN is home to the world's largest particle accelerator. With all these innovations and advancements, there is a chance the classical computers might run out of their strength. By 2026, the computing requirements will be much harder for classical computers to handle. This is where the quantum computer comes into picture. CERN openlab is working with worldwide research community to explore innovative computing solutions, and IBM has just joined as one of the latest members of this collaboration. Today we have with us Mr. Alberto DI Meglio, who is the director of CERN openlab, to talk to us about the importance of quantum computing and how it will aid research at CERN and help arrive at the answers the physicists have been looking for. DI Meglio is a graduate in aerospace engineering and has received a PhD in electronic and electrical engineering from the University of Birmingham. He also served as an officer in the Italian Navy and began his second stint at CERN in 2003. Welcome, Mr. DI Meglio. With advancements in CERN and you being synonymous with advancements in particle physics, there is a belief that classical computers will reach their limit by 2026. And this is where quantum comes in. But how do you think quantum will fit into the picture?
So very interesting questions. So first of all, I need to set the scene a bit, because you said the classic computer will reach the limit in 2026. Whoa, no, I hope not. So we are going to use classic computing for many years, many years to come. The current schedule of the Large Hadron Collider program and the experiment programs is expected to run well beyond 2030, and the data will be analyzed for many more years. So classic computer will be our primary means of simulation, data analysis, and computing for the next 20, 30 more years. But certainly there are a number of activities for which already now we see that the trend is going towards limitations of what classic computers can do. And although this might take quite a few years still, today is the right time to start looking at these problems and future challenges and prepare a lot of things. Prepare the community, raise awareness of these potential limitations and of the technology and what the future technology like quantum computing can do, and build the knowledge. So it is a steep road. Quantum technology and quantum computing are really an emerging technology. If you refer to the standard hype curve, quantum technologies today is at the very beginning, going up this steep road. So we need to prepare the community, the infrastructure, and the operations to exploit fully these technologies. So the start of a journey. It's an incredibly interesting journey. We see already that in certain areas, both in data analysis and in more theoretical physics simulation aspects, the possibility of using quantum computers will certainly give will certainly allow us to move beyond what we can do today. But there is quite a lot of work to do still.
Alberto, I understand, and I'm glad you spoke about data analysis, because is it true that quantum will be useful, especially in sifting through data sets for Higgs behavior?
So that is one use case. So working in collaboration with IBM, especially the researchers in the Zurich IBM Research Center, we have I cannot say demonstrated, again, this is very early work, but we have shown that there are situations, activities, especially in data analysis, where the inherent parallelism of quantum computing might help accelerating and increasing the computational efficiency of the ways we do data analysis. So the Higgs boson is one example. For example, this was an application of a special machine learning techniques adapted to quantum computers, and it has been shown that under certain conditions it is more computationally efficient than classic computer. But this applies to many other cases, so different types of particles, and especially our hope is actually to go beyond the Higgs boson or beyond what is possible today. So the Higgs boson is part of what is defined as the standard model of physics, this classification of particles and interactions. This is what we can observe today with the instruments and the computing capabilities we have. Now we have to go beyond. The standard model represents about 5% of the existing universe. Okay, there is another 95%. Okay, it's quite a lot. Today, this is generically classified as dark matter or even more dark energy. So, what the dark matter is actually made of is still a subject of theories. It is not possible today really to observe or to detect or to analyze data related to this dark matter. But if we can have much more efficient and sensitive instruments using quantum technologies and more efficient and more computationally efficient quantum computing means, then we can enter into that domain. It has to do with simulation. It has to do with data analysis. It has to do with classification. It has to do with anomaly detection, for example. So these are very, very interesting fields. You can imagine, instead of looking for something you can describe, maybe it is possible to remove everything we know, and what is left, the anomaly, is the new physics, is what we actually don't know and what we want to discover. So it's a sort of reversal of the model, and quantum computing, seems to be very efficient at implementing this kind of computing models.
Is there any other case study that is important to CERN at this moment? You're seeing much accelerated results, and that you want to talk to us through, and where quantum computer comes into picture.
So indeed, so as I mentioned, so the typical data-driven high energy physics process is composed of many different parts. So first of all, I mean, the main definition, the main distinction is indeed between the data analysis, so looking at the data that has been extracted from the real world, from the detectors, and comparing this with theories and simulation. So in order to understand whether we have indeed discovered something, we need to compare with the theories, and vice versa. In order to prove theories, you need to find the data supporting it. So these are the two main distinctions, and quantum computers might help in both. So for example, one example in simulation, we have talked before about data analysis. One example for simulation. Today, simulation is done using what are called Monte Carlo methods. Monte Carlo methods are very efficient for this kind of, for our kind of simulation, is radiation transport. But they scale not really well in terms of resources, meaning that if you want to have a bigger model and more precisions, you simply need to have more resources. So today already 60% of the high energy physics computing infrastructure worldwide, 60% worldwide, is, depending on the time of the year and phase of the experiment, is dedicated to simulation. So if we need to continue the current progress, it will not scale really technically and also economically, financially. So we are looking into ways of doing this differently, using machine learning, using deep learning, using artificial intelligence. So the next step is indeed quantum machine learning, quantum artificial intelligence, in order to increase the computational efficiency, decreasing the amount of resources that we need to use. And again, the expectation, given the way quantum computer works, is that this is a field of application for which quantum computers are well suited, and we are investigating exactly this difference in behavior and in computational efficiency.
You have reached a collaboration with IBM, and talk to us a little bit about the collaboration and why OpenLab decided to go with IBM.
So yeah, indeed, we have been collaborating with IBM for quite some time. Now, CERN OpenLab is a general initiative within CERN, exactly designed to run collaborative research and development projects with industry, with academia, with other research laboratories. And we have been doing this for 20 years. So this is even before I joined OpenLab. I'm today the director of CERN OpenLab, and I've been the director for the past 10 years. And we explore in CERN OpenLab the entire domain of computer science, data science, and information technology research, from data acquisition through distributed computing, databases, storage, and artificial intelligence, and so on and so forth. So we have been working with IBM for many years on a variety of technologies. But a few years ago, we started talking about quantum computing, especially we organized a workshop in 2018 exactly to bootstrap the investigation of quantum technologies for high energy physics, and IBM experts took part in this workshop talking about the IBM technology. So we started a set of R&D projects together, and more recently, given the state of the art of IBM quantum computing technologies and the projected roadmaps that have been published, we have decided to extend our collaboration into the actual use and test of the quantum computing devices. So this is very recent. It has been formalized just a couple of months ago. So now we are deploying our joint research program in this infrastructure. And again, for us, the simplest problem we could find would require 50 to 60 well-behaved qubits, which, I mean, again, we are not there yet, but the purpose of this investigation is exactly to understand how to adapt, how to reformulate some of these problems to take advantage of even of the current NISQ computers, but especially how the projected trend and roadmap will progressively enable our challenges, our problems to be effectively solved.
Understand, Alberto. But when you talk about deploying or engaging with IBM in terms of quantum solutions, as a director, and your equivalent would be a CIO in an enterprise, are there questions related to why we should account for technology that is still not reaching its inflection point now? And are there resistances in terms of mindset, in terms of locating budgets, in terms of moving ahead with such an innovation?
Yeah, definitely, yes. So, I mean, in some way, I mean, CERN is all about science and research. We're not a company, so we might have a different mindset and different timelines that your typical business enterprise. So for a start, yeah, I mean, all our activities, are generational activities. The LHC program started 20 years ago and will run for another 20 to 30 years. So our timelines are slightly different. And then our mindset is research. So we can we are used to, and we have all the means to onboard emerging technologies and in doing these early stage investigations as part of our standard way of working. Now, said that, of course, I mean, that's easier said than done. So we started in CERN with the creation of the CERN Quantum Technology Initiative, exactly to explore the current state of the art and to open up this emergent world to the entire community. We are routinely talking with hundreds of scientists and researchers and physicists, not only at CERN, but worldwide. And today, I mean, even from an education point of view, even from a background skills point of view, there is certainly a lack of awareness, a lack of knowledge, a lack of expertise. So we need to work on all fronts. We need to work on the R&D and technology. We need to work on the financial aspects. This technology is not cheap, for sure. And we need to work on the education and training aspects, and working with academia and with industry to have synergies, so that the next generations of scientists and researchers can start having quantum technology and quantum computing expertise as part of their early academic career. To make an example, if we open a position for doctoral students or early career researchers at CERN, typically for engineering or physics, we get many tens of applications for every position. For quantum computing, no, we are lucky when we get 2 or 3, and normally they don't come from a master degree in quantum computing. They come from physics or computer science with 6 months of specializations in quantum information science. So that has to change if quantum computers really have to become mainstream.
Understood. Also, are there any infrastructure changes that you have to make within CERN or with your other vendors to accommodate something like a quantum computer?
In terms of infrastructure, you mean? So this depends a bit on how the technology evolves. So traditionally, CERN, so it's a mix. So we have our own computing infrastructure on premise with a data center and computing center, and we are building a new one now. But also we exploit a worldwide distributed computing infrastructure, which this was set up 20 years ago. We call it grid, is essentially what is called today cloud. So we are used to work in this hybrid mode, on-premise plus distributed. Now the question is, will we ever have a quantum computer at CERN? So today, I would say my answer would be no. There probably is no point in adapting our on-premise infrastructure to use quantum computers if we can, seamlessly through standard or well-behaved software development stacks and infrastructure APIs, if we can exploit computers provided by technology providers like IBM, of course. Then I don't want to mistake that, in 50, 60 years ago, when computers were started building, even, very, very famous people said that probably in the world we would have only 3 computers in big centers. Nobody in their, sane mind would ever have a computer on their desk. They have been proven sorely wrong. So I don't want to say never, but today doesn't make a lot of sense. Now, if quantum computing technology evolves so that it doesn't need, very high-tech cryogenic infrastructure, very, sophisticated electronics, can work at room temperature, etc., then we can certainly reevaluate. But today, this is not the case.
Okay, so now with quantum tools at your disposal, what can we expect from CERN? What's coming up in the future?
So again, the next few years will be very interesting because, what we, if you allow me to simplify a bit, what we need to understand is indeed where are the areas where this mythical advantage can be found. Of course, we are not interested in simply reproducing or replicating what we can do classically on a quantum computer. So getting the same is certainly not interesting. So we need to understand where are these areas where in time quantum advantage will be actually realized. So we have an ongoing program of research to explore all the different areas in quantum machine learning, in simulation, in different application of classification algorithms, etc. And the expectation is that in the next 3, 4, 5 years, we will have a much clearer picture of the direction where we should, as a community, invest into, in partnership with the technology providers like IBM. And at the same time, according to the roadmaps that I've seen, we should be, in 3, 5 years' time, we should be near to getting out of the NISC regime. And at that point, we could probably, the idea is that the two research fields, the better technology and more understood algorithms and computing models will converge. And at that point, it will become incredibly interesting, because I'm pretty convinced that at that point we will really work beyond what is possible today with classic computers. That will be extremely exciting.
Absolutely, and we look forward to it, because with CERN's research, it's almost synonymous with what's possible next. Thank you so much, Alberto. It was really nice talking to you, and thank you for taking time out for this interview.
Sure.